Welcome back, and today we'll talk about the concept of energy, exactly what that means in the world of physics, and how we calculate some of the different types of energy that may exist around us. So first of all, what is energy? It's a difficult thing to actually express. I like to call energy the currency of the universe. Currency is another fancy word for money. I want you to envision how money works, currency or money, right? Typically, you can have lots of money or you can owe lots of money. It's kind of like a zero bank balance is like a straight line, $0. But if you gain money, then your bank balance will go up. If you lose money, your bank balance will go down. If you lose more money than you have, we say you are in debt. And so it's like debt means not having enough money, or sort of less than zero money. And when you have extra money, the word we like to use in the world of finance is credit, right? You have credit, so you have money in the bank. So it's possible to have $500 in the bank, but owe $500 of debt, and then that means that you basically end up with $0. So this concept of having some and owing some and then putting it together to figure out exactly how much money you really do have. If you owe less, let's say you only owe $200, but you have $500, we would say that you are actually in possession of $300, right? You take away the debt. Debt is like a subtraction of money, and credit is like an addition of money. And that's how money works. And what we do is we use money to determine how wealthy someone is, talking about their wealth. Energy sort of works the same way. If we envision energy as sort of zero energy, means kind of a flat line, call that zero energy. If you can either get energy or lose energy, just like money. So if you get energy, you turn into a positive amount of energy. If you lose that energy, you go back to zero. It's even possible, we think, to owe energy to the universe. So somehow you represent a negative form of energy. So energy, very much like credit and debt, like in the world of finance, you can also think of it as credit and debt of energy. So instead of measuring your wealth, we're measuring what's called the amount of energy in a system. And so it's kind of like a bookkeeping way of looking at the universe. Everything that happens in the universe causes energy to change somehow. And as the energy changes and fluctuates up or down, we get different amounts of energy. So we could think about a simple process. Whenever something changes the way it was existing, then we think that energy must be involved. So if we imagine a simple process, like a hill and a ball, well, if we freeze the picture, right now that's the way it is, and the ball is sitting there. But we know that if we let the picture run on, if we turn time back on again, this ball will not stay there. The ball will do something. It will roll down the hill. And anything that happens in our world means that somehow there's going to be an energy change. Either energy is going to be added or energy is going to be taken away. And so a ball rolling down a hill is an example of energy changing. Instead of a zero amount of energy, the energy will fluctuate. Right? Car. When a car is driving on the road, the car has an engine, and inside the engine there's gasoline, which is a molecule, and that gasoline is being burned. or what we call combustion. And in the process of combustion, we get a change of energy. Energy that was somehow locked up inside the gasoline now can be turned into energy causing the car to move. So those are two examples. Even you use energy to do all the things that people do. And you have a fuel. The fuel that goes into your engine is glucose, or sugar. Right? Sugar is the main source of energy for humans. And if we eat sugar, then the combustion of sugar, and it's exactly the same kind of reaction, just happens in a slightly different way with more steps involved, so we don't blow up. The combustion of sugar will cause our energy to change, and we can use those changes of energy to do things like walk upstairs, or our muscles to contract. And so it's very important in physics to look at the way that energy changes whenever something is happening. And so it's so important that we give it a special type of name. And the word we give is called work. Work means a change in energy. So anytime the energy of something changes, work is done. So now you might think work is like, when you shovel a load of gravel off of a wheelbarrow. Well, it is, because you've changed the energy of the gravel. Anytime something moves or changes its position or is in a different state after than it was before, means that very likely some work has been done somewhere. Work is the change in energy. Okay, let's talk about some of the different types of energy, or different ways in which we can account for it. Just like the world has different types of currency, there's American dollars and there's Japanese yen, there are French francs, and now there's euros. All of Europe uses the euro, and there are all kinds of money. Some people still use other things to represent money, like they trade things of value. Like, for instance, maybe a collection of stamps might be worth a lot of money. And so we use all different ways of describing money, and we also have all different ways of describing energy. So if we look at some of the types of energy that exist, there's a lot of different types. We'll just look at a few examples. There are two main groups, though, and the two main groups are what we all call kinetic energy, and potential energy. Kinetic energy is basically caused by, or the result of, motion. Anything that is moving has kinetic energy. A ball rolling down a hill, a duck swimming across a pond, a rocket going to the moon, a car driving on the highway, etc., etc., etc. Even a person waving their hand back and forth. Any kind of motion or moving is what we call kinetic energy. There are certain kinds of energy that are caused by motion, and the most common one is heat. Heat is a form of kinetic energy because heat is caused by, if you think back to grade 9, you learned that the particle theory of matter. All things are made of particles. The particles have spaces between them. There are forces between them, and the particles are always moving. Heat is caused by moving particles, atoms, molecules, and so on. This kind of moving is actually more described like a vibration rather than going from place to place. It's more like just vibrating back and forth. So the particles inside an object are moving around. They're like jiggling with a vibrational motion in all different ways. Jiggle, jiggle, jiggle. And so heat, because it's due to motion, is a kind of kinetic energy. Now, Potential energy is energy that, we like to use the word stored up energy, that's kind of sitting there waiting to be released, stored energy. Energy that isn't actually making anything move yet, but can be used to make things move if we want to. So examples of this might be the electrical energy that's in a battery. It's just sitting there in the battery waiting to happen. And if we just leave the battery alone, it just sits there and does nothing. But if we hook up the battery to a circuit with a load, we can then change that electrical energy that's stored in the battery into kinetic energy by moving the electrons through the circuit. So electrical energy can be stored as a potential energy, and we could also think of electrical energy as the motion of electrons. So technically, it could kind of go in both categories, but if we think of the battery as the example, then electrical potential is the energy stored in a battery waiting to make electrons move. Okay? Another kind of energy that can be stored would be something like elastic energy. When you stretch something that is stretchy, we say an elastic, but it doesn't have to be an elastic. It could be any kind of rubbery substance. You can stretch socks, you can stretch elastics, you can stretch a bungee cord, you can stretch all kinds of things, anything that's stretchy. When you stretch it and you hold it there, you can feel it pulling against you. And so that elastic energy is energy that is potential. It's stored in, say, the stretchy piece of bungee cord. And if you let go, it will move. It will snap back into place, and it will cause kinetic energy. So you can see how almost all of these potential energy things that I'm writing over here can be turned into kinetic energy if we want them to. And that's kind of the secret to how we use energy. But there are many other kinds of potential energy. Another one is gravitational energy. If you take a heavy object and you hold it up high, as long as you hold it there, it'll just stay still. But if you let it go, it will fall. Gravity will cause it to move downwards and accelerate, and the energy that it had, because of being up so high, will be released. In fact, it will turn into kinetic energy as the object moves down towards the ground. So electrical energy, elastic energy, gravitational energy, lots of different ways of describing kinds of energy. One more that's a good one is chemical energy. Inside objects, there are molecules and atoms which are held together by chemical bonds. You learned that in grade 9 and 10. Well, these bonds have energy. And if you break apart the bonds of molecules, you can release some of that energy. So the gasoline in the car is a chemical. When you combust it or burn it with oxygen, the molecules in the gasoline, octane, nonane, hexane, heptane, these molecules are long molecules that are broken apart. And when they're broken apart, the energy that was in their bonds, the energy that was chemical, can be used by the car's motor in the combustion process to cause the car to move. And so what you can see is there is a relationship between potential energy, stored up energy, and kinetic energy. Kinetic energy. And this relationship is what we're going to discuss in detail, or in a little bit of detail, in this particular unit. Potential energy is used to make things move, and if you move things around, you give them potential energy. So let me give you an example using two kinds of energy. Kinetic energy, and instead of just saying potential could be any one of those, let's use gravitational potential energy. Let's take a look at an object. Here it's a big rock, and you're holding this rock just over the edge of the cliff. So So at first, let's call it time number 1. The rock is there. It's not moving. You're holding it still, which means that the kinetic energy of the rock is 0. It's not moving, so it has no kinetic energy. But it would be able to move if we let it go, which means that gravity is giving it energy. So what it has is it has what we would call gravitational potential energy. So it's a certain type of potential. Gravitational potential energy. It has that. It has some, and we know that because if we let it go, it will move. It will do work, or at least gravity will do work on it. So let's say we do let it go. And let's say that after a while, it falls all the way to the ground. It's just about to hit the ground. A millisecond before it hits the ground, time number 2. Let's look at what it has here. Now it's moving fast, right? As it's fallen, it's gotten accelerated faster and faster. It's moving fast. So now that means it has kinetic energy. But it's about to hit the ground, which means that gravity is not going to be able to do anything to it once it hits the ground. And so it doesn't have any more height. It has lost all of its gravitational potential. It's lost its gravitational potential energy. Oops, better spell that right. Potential energy. In fact, we could say that if it's going to, once it hits the ground, 0. No more potential energy. So you see what's happened? It started off with no kinetic and gravitational potential, but the gravitational potential energy was turned into motion as it fell through the air, and it became kinetic energy. So you can see how this relationship I talked about is playing out. Now this change is happening gradually as it falls. So if we were to examine position number 3, say some spot right here in the middle where it hasn't quite hit the ground. At position number 3, it's falling, so it is moving. So it has some kinetic energy. But it's also still got some height. It hasn't hit the ground yet. It has some height, so that means it also has some gravitational potential energy. I'm just going to shortcut that so I don't run out of space. It's got a little bit of both. So in position 1 at the top, it has 0 kinetic and all gravitational energy. At the bottom, it has all kinetic and no gravitational energy. And in the middle, it has a little bit of both. And so you can see that at the top, as it begins to fall, some of the gravitational potential energy is being turned into kinetic, and so the gravitational energy is slowly dropping. But the kinetic energy is increasing because, don't forget, objects go faster and faster as they fall. They accelerate because of gravity. And so the longer they fall, the faster they go. And this is what we mean by this trade-off in energy. Now, the important rule is called the law of conservation of energy. Just like if you have money And you go to the store and you buy something and the money goes to the store. And then the store uses that money to pay for their lighting bill or electrical bill. And that money goes to the electric company. But then the electric company pays that money to one of its workers to fix one of the telephone or one of the power lines. And that worker takes that money and he goes to the gas station and he pays for some gas. And then the gas station owner takes that money and he goes off to Walmart and buys a new sweater. And then Walmart takes the money and pays it to somebody who happens to be running the store manager. You see, what happens is the money keeps going all over the place, but it never disappears, and the money never changes. However, whatever that amount of money was, it stays the same. Even though you might pass that money to a whole bunch of people, you might even split it up and give some to one person, some to another, and some to another, but it's still all there. Money doesn't just disappear. It's always around. And the same is true of energy. Energy cannot just disappear. So the amount of energy that's in a particular situation has to always be the same. Okay? Now there's a couple of ways of writing this. One of the ways that people write it, and you may have seen this, is that energy cannot be created or destroyed. Does that sound familiar? Energy cannot be created or destroyed, comma, it can only change forms. You can change gasoline chemical energy into kinetic moving car energy. Okay? I guess we should put the word only here. It can only change forms. But you still have the same amount, you see, when you add it all up. Okay? Now what I like to do in physics, because we're going to start using this to solve problems, is think of it a slightly different way. The way I like to think of it is this. The total energy at any point in a scenario. The word scenario just means something happening. A ball falling off of a cliff, a hockey player shooting a puck into the net, whatever. The total energy at any point in a scenario is always the same. Okay? Another way of putting it is that the total energy, and this is how I'll tend to use it the most, the total energy at any point, call it point number 1, is the same as the total energy at any other point. So it's the same at any other point. So that could be point number 2, or point number 3, or however many points you want. Total energy is always the same. So if I draw a picture, and I'm going to draw a picture of a roller coaster that starts here, goes down, goes up a little loop thing, goes down again a little further, and then it goes up like this, and then it comes down, and then it levels off. So let's pretend that that's a roller coaster, and here's a little car on the roller coaster. Now, if we watch the scenario, the roller coaster will follow the path. But what we can do is we can look at different spots, and they can be anywhere. We're just going to pick them. I'm going to pick spot number 1 to be the start. I'm going to pick spot number 2 to be right here at this point, spot number 2. And I'm going to pick spot number 3 to be, actually, you know what, I'm going to change my picture just so I can prove a point. I'm going to make this part of the roller coaster come down and all the way down, and that's going to be the ground. So that's how high the ground is. And we're going to call spot number 3 the spot right down there on the bottom. 1, 2, and 3 spots. Now, if we use our rule, the total amount of energy at spot 1 has to be the same as the total amount of energy at spot 2. Okay? So, that means if we're looking at the kinetic energy and the gravitational potential energy, at the top we have gravitational energy, Eg. So write somewhere in your notes that Eg stands for gravitational potential energy, because that way we don't have to write this out every time. And then I'm going to also use a little e with a little k, which of course will stand for kinetic energy. Okay? So there is going to be Eg here. But at the very beginning you're not moving. So there is no Ek, no kinetic energy yet. If you add them up, whatever the Ek is and the Eg, you get the total. At position number 2, because you have gone down a little bit, you don't have the same amount of Eg anymore. Your gravitational potential energy is less because it's related to your height, how high you are. But you still have some height. So Eg, some, and now the car is also moving. Even if you stop the action at position 2 and you take a snapshot, you know that in that snapshot, the car wasn't standing still. The car was going down the hill. It was rolling. So it has to also have some Ek. But if you add these up, they still add up to the total energy, which the rule says can never be the same, or must always be the same, sorry. The difference is you've changed it up a bit. At the top, you had all Eg and 0 Ek. Now you lost a little Eg, you gained a little Ek, but it still adds up to the same numbers. Now at the bottom, you can see how we've reached the bottom of the roller coaster. We have no more height, which means the Eg is now 0. No Eg. Maybe I should just write that like I did the first time. No Eg. No Eg. But when a roller coaster hits the bottom, it doesn't just stop. It's got a lot of speed built up because that total energy is still there. But guess what? Now it has lots of Ek. Right? Lots of kinetic energy. But if you add it up, they still equal the total. So you can see how the total energy has to do with the sum of, or the adding up of the kinetic energy and the potential energy. A roller coaster car can have some of each as it moves through the course, or at the very start it could be not moving at all and have all Eg and no Ek, or at the very end it could have no more Eg, no more height, and all kinetic moving energy. But if you add them up at any spot, those green totals will still all be exactly the same number. And that's what this law of conservation of energy is trying to tell us. The total amount of energy at any point 1, 2, 3, or 4, 5, 7, 12, is always the same, even though the kinds of energy might be different. All right? So that's the law of conservation of energy. In the next video, we will look at how we can actually start to use some numbers to describe these things. And we'll take the same example of this roller coaster, but we will put numbers in, and we will see if we can't figure out what the actual numbers would be. Okay, so until next time, maybe you just want to watch this a couple of times and get the idea behind it, so you don't have to sweat it. There's not going to be any assignment on this particular video, but there will be after the next one or two.